So let's start again. It is my pleasure to introduce Uri Shalit. Uri is an assistant professor at the Technion in Israel. He received his PhD in computer science from the Hebrew University in Jerusalem. And after that, he spent some time as a postdoc with David Sontag at NYU and MIT. His research has two main themes. So one is applying machine learning in healthcare. And the second one is the intersection of machine learning and causal inference, which is also the topic of today's talk. And before I give the floor to Uri in just a second, I'd like to mention that after the talk, there'll be an apéro just outside, and you're all very welcome to join. And now, without further ado, I'll give the floor to Uri.
Thank you. So thank you very much for having me, and thank you everyone for coming. You reminded me about half of my research, which I won't talk about today, which is the machine learning for healthcare part, where I do very applied work. So if anyone is interested in that, I'm happy to talk about that after the talk. So let's start. So machine learning has seen some remarkable successes in the last few years, mainly about learning to classify. For example, ImageNet, all the breakthroughs since 2014, amazing success. This has also been applied to healthcare, for example, identifying retinopathy in retina images. This is great work from Google. Voice, text, and so on. Machine learning also had amazing success in the last few years in learning to act, not just learning to classify. For example, learning to play Atari games, learning to play Go. This has been really impressive, and I think drew a lot of attention to this field. And let me say that learning to act when a simulator is available, as in Atari and Go, and we'll see later why this is important. So what's the next step, or a next step? What are some things we can't do yet? So who here knows the difficult cows example? Okay, I'll show it. I'll get into it soon. For example, identifying objects in a priori unknown contexts where humans succeed. So this image turns out to be somewhat difficult for many state-of-the-art image recognition systems. And also, how to act optimally when you don't have access to a simulator. Okay, let's say you observe data from a hospital of how patients are treated, let's say in an intensive care unit, and from that data you want to learn how to treat patients better. That is not yet something that reinforcement learning can robustly do. And I'll talk about some of these things here. So the outline, I'll have three parts. I hope to get through at least two of them. The first, I'll be talking about something called unsupervised covariate shift. It's learning models with independent residuals. Second one is about, so this will be about classification or regression. The second is about action. It's off-policy evaluation in difficult reinforcement learning scenarios. And the third, if I'll have time, is about compositionality as a causal mechanism, and you'll see what I mean if I manage to get there. So let's start with unsupervised covariate shift. And this is a paper on arXiv with my student, Daniel Greenfeld. So we've seen this. We can do really well on tasks of classification, prediction, and so on. But there are failures. So this is an easy cow. How is it easy? You take this image, you give it to a state-of-the-art image classification algorithm, and it tells you that there's a cow, cattle, mammal, grass, livestock, and this works well. And this image was not seen before by the algorithm, so this is a success in the test set. But when you show the same algorithm, this cow, which I think all of us would recognize as a cow, it says there's no person here, a beach, water, sand. It says many interesting and correct things, but it misses the cow. And the reason, we suppose, and this is from Pietro Perona's example, is that in the training set, cows usually were not observed on beaches. So this is a difficult cow, but for us it's not difficult. We do it really well. Also, these examples, we have these people, these sports players classified on the top as a basketball, on the bottom as a ping pong ball. There's no ball here. And again, this is a severe failure of the classification algorithm because of biases in the data set, because of many, many reasons, which I will not go into all. So in both cases, though, the test set is in some sense different from the train set. And we want to succeed at least in some cases where the test set is different from train set. For example, we know humans could succeed in such cases. Even if you've never seen a cow on the beach, you have no problem recognizing this as a cow. Okay, so that's the motivation or the inspiration. And the problem is how to learn models which are robust to a priori unknown changes in the test distribution. Okay? So we'll think about it this way, we'll formalize this way. We have some source distribution over x and y, PS, and we want to learn a model that works well on some set of unknown target distributions, Q. Okay? And PS is a part of Q, and we want to succeed on them. And of course, we will have to restrict Q in some way for this to be meaningful. Yeah, and this, by the way, is inspired. This slide, this drawing from something from Nikolai Mainshausen, which is not here, right? But I liked his slide, so I took this idea. So we want to learn a model that works well on all target distributions P prime x, y in Q. And the goal is to classify, so we need to know something about P of y given x. And what is Q? We first restrict it this way. We assume something called, in machine learning, this is called covariate shift. We assume that the conditional distribution of y given x is the same for all models. Okay? And we'll have further restrictions soon. Now, this is not challenging at all if learning the conditional distribution is easy. If we can easily get the conditional distribution, then we're fine. But often this is a hard task. We don't have the right model, the true model of y given x. In our hypothesis class, we only have approximations, and that's where this scenario is interesting. And so we call this, I haven't seen this before, people have talked about it, but I haven't seen this specific name, we call it unsupervised covariate shift, because we assume we have no samples from anything except P of S. We only have samples from P of S, but we want to be good on all the set Q of possible targets. Okay. By the way, feel free to ask questions. I have no problem with that. Okay. So we want a model that works well, even when the underlying distribution of instances, when P of x changes, right? If P of y given x is the same, that means that we have to assume P of x changes. And this is a reasonable task if P of y given x is stable. Okay, if we can actually believe that even if we change x, P of y given x is the same. For example, if we change the pixels of an image, and now we have a cow on the beach, P of y given x, the probability of a cow given x, might be the same. And when does this happen? This happens when we have causal mechanisms. When you have a causal mechanisms from x to y, one could assume that it is stable or more stable than in other cases. So if the causal direction is going from x to y, we might think that covariate shift is a meaningful task, is something interesting to do. Okay. And people have looked at this problem. So two papers, one is the anchor regression from Rothenhausel and the other graph surgery paper from Subaswamy and Saria. And they took a causal graph approach to this problem, saying, basically drawing the causal graph, tying x and y together and saying all kinds of interesting things about that. We will take a very different approach than the causal graph approach in this case. Okay, now let's get this. And what we propose to do is learning with an independence criterion. And what do I mean by that? If we believe that x causes y, again, that's our assumption. X causes y, that's why talking about covariate shift is interesting. And we can write the structural causal model as follows. We can say y equals f star plus epsilon. Epsilon is some noise which is independent of x. And f star, we think about it as the mechanism tying x to y, the true mechanism. And epsilon is independent additive noise. So this is an assumption we're making, that the noise is additive. It need not always be true. Okay. Now, if we just stare at this and move things around, this means that y minus f star of x is independent of x. Okay. Again, the true model. So the residuals between y and the true model are independent of the instances x. And in 2009, Mui et al. Suggested learning the structure of causal models by learning functions where y minus f of x is approximately independent of x. Okay, they suggest this as a learning criterion in order to learn the structure of a causal model. And that will be the idea we'll follow. And for that, we need a non-parametric measure of independence. We need a powerful way to measure independence. And we will use something called the Hilbert-Schmidt independence criterion. Okay? So again, we'll try to learn models F whose residuals, y minus f of x, are independent of x. And how will we measure independence? Using the Hilbert-Schmidt independence criterion, which I'll introduce now. So just a question, who here has heard about the Hilbert-Schmidt independence criterion? Okay, most of you have not. Okay, so now I'm defining this, and this will be the major technical tool we'll use in order to learn models that are robust. So if x and y are two metric spaces with some joint distribution, and g of x and g and y are reproducing kernel Hilbert spaces on x and y, who induce kernels k and l. This is standard RKHS stuff. And HSIC, Hilbert-Schmidt independence criterion, measures the degree of dependence between x and y. Okay, and I will not go into the entire definition, but here's the empirical version of HSIC. So if I have the kernel K and the kernel L, which correspond to the kernels K and L above, if I have the kernel matrices K and L, so I'm overloading notation, I could look at the trace of the product of matrices K, H, L, H. Okay? And H is just a centering matrix. Okay, so it's a very simple matrix. This turns out to be a very nice measure of dependence or independence between x and y. Okay? So, and there's a lot of theory around this. Basically, Gretton et al. Proved that the empirical estimate converges nicely to the population estimate. And they also proved that this is zero in the infinite sample limit. This is zero if and only if x and y are actually independent. Okay? So you can think about this as covariance on steroids, right? Covariance is zero if two variables are independent, their covariance is zero, but zero does not imply independence. This actually goes both ways under some regularity conditions. And it is actually, you can formulate this as a covariance condition, but we will not go into that. Okay? So we have here a way to empirically measure dependence between two variables x and y, which depends on defining the kernel functions and the kernel matrices k and a. And we can use this to learn with this criterion. So, and this is what we do. So if we have some hypothesis class H, these are the functions we want to learn to predict y from x. Classic machine learning would be minimizing the expected loss of y and hx for some loss, for example, the squared loss. Okay, so this is classic empirical risk minimization. Learning with HSIC does something else. It says let's minimize over a class the dependence measure HSIC between x and y minus h of x. Okay, so let's see, does this work? The residual, I want my residuals to be independent of x. That's a very different objective function from the standard ERM. Okay. Questions so far? Okay. And so this was proposed in 2009 for learning for a very different purpose than what we're using it. And recall that y minus f star is independent of x. That's our assumption. F star is the true function. And so it's very easy to see that if we find some h star for which y minus h star is actually independent of x, then we found the right function up to an additive bias. So basically, in the infinite sample limit, if we manage to turn this into zero, we found the right causal model up to a constant shift b. Okay, so at least that we know. So infinite samples, if we have the true function, then we're good, up to the additive bias term. And one way to think about learning with this criterion is a non-parametric generalization of how residuals are orthogonal to the instances when you do OLS. So if you do ordinary least squares, right, the residuals are orthogonal to the x. So here we're extending this using this idea of HSIC. Okay, so you have this. And what we do is we just optimize this. How do we optimize this in practice? We do stochastic gradient descent using mini batches to approximate x. Okay, so if you have a mini batch, you can calculate the kernel matrices over the mini batch and take the gradients. It's all differentiable and very easy to do. And we have a PyTorch implementation for that if anyone's interested. Okay, so you could optimize this quite easily. But what can we say about this? Okay, so okay, it's differentiable, that's nice. If it's 0, then we're good. But can we learn this? Is it learnable in the statistical learning sense? So does minimizing over a sample lead to generalization? We don't have infinite samples, we have finite samples. And the answer is yes. If the kernel expectation is bounded and we have a spherical Lipschitz kernel, for example, the RBF kernel, then we can prove that learning over a finite sample actually leads to generalization in the statistical learning sense of using a Rademacher complexity and so on. We can prove this by reduction to some weighted learning problem over pairs. That's how we do the proof. And then it ends up being reduced to standard learning theory after we look at it as a learning problem over pairs of x prime. Okay, so this is the first result that just says, if we want to use this objective function of minimizing the dependence between the residuals and x, learning from finite samples isn't ridiculous. It might make sense. And if it's 0, then we're good, but we want to be robust. Our goal was to say something about what happens if you change the distribution of x's. And our claim is that this loss function is better suited than standard loss functions for this task. And what we can prove, so we'll now have a theoretical result showing this in a certain scenario. So now we'll define more specifically what is the set Q of distributions that we want to be robust against, that we want to be able to work well on. So recall, we're only changing the marginal of x because we're assuming y given x stays the same. And we'll define set Q as the set of density ratios, P prime over PS. PS is the source, such that P prime is positive, the expectation is 1. Basically, this means that they're absolutely continuous with respect to P source, and that the density ratio function is a member of the RKHS. Okay, so this is the main part here. We're limiting what density ratios are we allowing. We're allowing density ratio functions which are in the RKHS G of x, and we can control the size of this RKHS by controlling its norm. Okay. So Q is a family of density ratios. Family of density ratios of densities. Okay, that's just family of density ratios. Okay, and we control the size of Q by something we will call mx, which is the maximum norm of functions in this space. Okay. Questions about this?
So just if you have this condition in the middle, that it's equal to 1, the ratio in expectation. Oh. So the condition in the middle that the expectation of the ratio is 1, does that include quite general covariate shifts, or is that already quite a substantial restriction?
The absolute continuity. Basically,
that's
it means,
all. Because I would have thought, okay, if P prime has quite different center, right, than PS, then this will not hold, right?
Well, as long as they have as long as it's not 0 on some part, then it will be fine.
Okay, maybe just...
Okay, we have other, by the way, this is not the only set. We can look at other sets. We have other results beyond this set, but well, we can take it, talk about this later. And what we can show that for this set, we can actually bound the error for all these a priori unknown functions P prime. Okay, so we don't know what our test set will look like, but we know it won't be too radically different because the set Q bounds this difference. And we can show that for any hypothesis H of x, the MSE ordinary mean squared error on the target distribution, P prime, is bounded by the following. The H6 term multiplied by, we'll see what these are, plus a bias term, which is very easy to estimate because it's on the source, plus the irreducible noise epsilon squared. What are these mx and my? My is the maximum norm of the functions in gy. That's the other, H6 has 2 reproducing kernel Hilbert spaces, And the way to think about it is the larger my, the better we can approximate this, the residuals. So we allow more difficult, more complicated residuals to exist. And mx, as we said, controls the size of the target set Q. So when we think about it, is minimizing HSIC minimizes some upper bound on this target loss, which we cannot calculate in advance. And we can show that this is actually, in most cases, much smaller than if you just do the MSE, the ordinary mean squared error. Then your bound will be much worse because it will be basically the worst density ratio. Versus here, we have just the norm of the density ratio function, which is typically much, much smaller. Okay, so this justifies, in a sense, why minimizing HSIC, which is what we can control here, plus getting the bias term right, bias term is just a constant, can give us good generalization on the entire set Q of different distributions P of x. Okay. And of course, HSIC is evaluated on the source. So we learn once and we want to be successful everywhere, at least to a degree. So this is the basic idea. We have a similar result for a different set of Q, which is if you only allow your target to be on subsets of your original function space. So you're saying, I'm trained on the entire set of images, but now I want to be good just on a subset of the images, which I might have been not cared about too much earlier, but now I really care about them. So we have a similar kind of flavor of result for those kinds of covariate shifts. Okay, so this is in theory, but does it work? So we ran several experiments. One is a bike sharing experiment, which was introduced in the Rothenhauser paper for anchor regression. And we compare with them and with graph surgery from Shulam and it's not Shulam, from Subaswamy, Shulam, and Suchi. So we train on what we have here. This is data from a bike sharing. I guess some people here know more than me. A bike sharing service here in Switzerland, and want to predict demand. And we train on 3 seasons and test on the 4th season. Okay, so the target is different from the source. Is this a covariate shift scenario? We're not sure, maybe. It depends on the X. We have measurements of all kinds of things which reflect season and so on. And what we see is we compare ordinary least squares, anchor regression, surgery is the graph surgery. In our case, first what we saw in this data is the ordinary least squares does pretty well. The good old OLS. But we do see that that we often do better when train on 3 seasons and test on the other. HSIC often has a better error than the other methods. Even though these methods, AR and surgery, do assume something about the causal graph, they take advantage of a bit more knowledge than what we do because we're not looking at the graph, we're just trying to minimize this new criterion that says your residuals should be independent of your predictions in a non-parametric way. And another experiment we did, which was inspired by work from Christina and Nikolai, is something called rotated MNIST. So we have ordinary MNIST, the digits, and then the test set is rotated uniformly at random from minus 45 to 45 degrees. So this is how the test set looks like. And again, we trained once on the source of an ordinary MNIST, and now our test set looks different. The distribution of the instances is different. And we compare our criterion with standard cross-entropy loss. And first we try a convolutional neural net, and we see that on the source, we basically have the same performance. On the target, we do have somewhat better performance for the HSIC. This is the interquartile range, this little box of our predictions. And then we replicate this for many other architectures. Okay, we try lots of different architectures for the neural nets. And what we keep seeing is that the HSIC criterion consistently performs better somewhat on the source, but very much so on the target set, which means there is something happening, something going on here, which is we're not completely wrong. or we're not only right in theory. And we also have more experiments on color dimness, which I'm not showing. So any questions about this experiment? So in general, learning with this independence criterion, so intuitively, if y minus h of x is independent of x or almost independent of x, that means there's no information left in x to learn from. Like we took everything away already. The model h left nothing to do. So I think that's an intuition that might justify why this is a good thing, but we are still working on understanding the full ramifications of this idea. For example, it's not obvious why you want to be independent of all of x. Maybe you just need a part of x, and that's enough. Okay, so any questions about this? Okay. So that was about learning models that could be robust to a priori unknown changes in the source distribution. Yes?
Just one question before you move. So I'm wondering, how does this method...
Scary.
Do you know how does this method compare to directly minimizing this like distributional robust objective? Like you do the mean square error over p, but p is you put the p constraint to be close to the q in some distance, k or divergence or f divergence. Basically, John Ducci kind of line of work. If you just minimizing this distribution robust objective, how does it compare to your method?
We are still working on this, and the specific of the John Ducci work, they're looking at a different set Q. We still could not make their code work for our case. But yes, that's a good question, and I hope eventually we'll get that. Yeah, it's yeah. I hope I'll be smarter in a few months once we manage to make it work. Any more questions? But it's right. That is a natural comparison. Wow. Okay. So now we'll move to a different failure case of current machine learning, which is off-policy evaluation in difficult reinforcement learning scenarios. And this is a paper now in AAAI with Gaita Holtz and Shai Manor from the Technion. And just a question, who here knows the basics of reinforcement learning? Okay, most people do. Okay. So, as I said, I work in healthcare, so I'm motivated by healthcare problems. If you think about physicians treating a patient, they make ongoing decisions. They treat, they see what happens, so they take an action. The patient states changes, they're still alive, maybe they're not still alive, and the doctor sees that and acts on it, and so on and so forth. And this maps very nicely, as many people have noticed, to reinforcement learning, where you have an agent acting on an environment, getting a reward, seeing the state, and so on. And so people have been trying to apply reinforcement learning to healthcare problems. And just where do the reinforcement learning ideas meet causal inference? So from a causal inference perspective, reinforcement usually assumes, assumes we can intervene directly. Okay, if you're playing Atari and DeepMind, you can just change whatever you want. You take whatever actions you want. So coming from causal inference, RL, you could frame it, if you're not generous, as how to experiment optimally in a dynamic environment. You want to learn how to experiment in the best way possible. Looking at causal inference from an RL perspective, causal inference usually deals with cases where we cannot intervene directly, or at least the causal inference work I'm used to, and usually focuses on single point-in-time actions, not dynamic actions. So it's mostly about off-policy evaluation of a simple policy, such as treat everyone. And where do these two meet? So if you're doing off-policy evaluation of data which came from a dynamic environment with ongoing actions, but we possibly do not have access to the same data as the agent, That's where we kind of need both the reinforcement learning aspect, because you have a dynamic environment that you need to deal with, but also the causal inference aspect, because you cannot intervene, you need to use observational data, and you might not observe all the data, so you might have hidden confound. So I think that's a fruitful or potentially fruitful place where these two meet, reinforcement learning and causal inference. And an example is if you want to learn from records of physicians treating patients in an intensive care unit. So you have to be off policy. You cannot experiment on these patients. It's very dynamic. The doctors often do something that says, let's put the patient in this state, because in the future, being in this state will allow me to do that. So there's interesting dynamics going on. And of course, we want to be able to help the doctors and do better. And some work has been made that was misguided, okay? People have tried applying reinforcement learning to observational intensive care unit without thinking about the causal inference aspect, okay? And to answer that, there was this paper from my former postdoc group, from Sontag's group, Guidelines for Reinforcement Learning in Healthcare, which was trying to kind of tell the reinforcement learning people that in some cases you have to think about causality, because otherwise big mistakes could be made. Now, one technical place where we can all live happily together is something called the POMDP. So in RL nomenclature, hidden confounding, which is like the main issue of causal inference, can be described by a partially observable Markov decision process. And I'll define it here. So I will not go into the full technical definition of a POMDP, but you have a finite state space, finite action space, an observation space, which is not what, in an MDP, you just observe the state. Here, the assumption is you do not observe the state, you observe some space, which is a function, you have an observation function. So you have some function, not necessarily one-to-one, not necessarily known, that takes the hidden, unobserved state to the observed state. And you have all the other ordinary reinforcement learning aspects. Okay, so really the important part is you have a state, it's finite, the process is Markov with respect to the state, but you observe something else. You observe Z and not U. Okay. And just to draw the graph, so you have, this is without dynamics, you have the state U, which generates the action A, and both of these together generate the reward. And what's called the state in reinforcement learning is called a confounder in causal inference, and what's called a reward in reinforcement learning is called an outcome in causal inference. And this is still without the observation, but we'll get to that soon. Then we have something we call pi b, which is this arrow. So how are the actions generated? In causal inference, it's called the treatment assignment process. In reinforcement learning, it's sometimes called the behavioral policy. So some agent behaved in some way, and you observe some things from their policy. Okay, so the examples will be the true state will be the information available to the doctor. The actions could be medications or surgical procedures. The reward might be mortality. And the treatment assignment process is just what the doctors actually do. They see the information, they have some policy they enact in the world. Okay, so this is without the observations. Now we add Z. Okay, so we added Z. Z is the observation. And sometimes in causal inference, it's called the proxy variable. And you might think of it in the healthcare case as the electronic health record. So the electronic health record reflects something about the state. You might have many measurements in the ICU, but it's not what the doctor sees. The doctor sees the patient. They have possibly more information than what we have. We only have access to Z and A and R. We do not have access to U. And of course, to make it harder, there's dynamics, okay? So the next state is a function of the previous state and the action taken, okay? And so on and so forth. Okay, so questions about this POMDP model? So this is a standard POMDP model, but as a causal graph. Now, we observe data. Our assumption now, we will assume in this section infinite samples, because even in infinite samples, this problem is really hard. So we observe data drawn from pi b. So as in, the doctors behave in some way, this induces a distribution on this state, they behave further, this induces a distribution on this state, and all the rest. So we have an entire distribution over everything, which is induced by the behavior policy pi b. And we observe data from that, but we don't get to see the state. We only see Z, A, and R. What do we want to do? We want to propose a new policy and say that it's better. So we want to evaluate a new policy, which we'll call pi E for the evaluation policy. So we want to evaluate a proposed policy. Let's say we want to implement a system in the ICU which tells physicians, oh, you should do this, you should do that. Now that system takes as input not U, but Z, right? U is the unobserved. So we can only learn policies that use the data that we have, which is Z. So our evaluation policy is different. And also, of course, it might have, in details, it might be very different from pi B. So we observe data from pi B with UT unobserved. And once we evaluate some proposed policy, pi E of ZT, in terms of policy value, standard reinforcement learning, discounted policy value. And how can we do this? So how can we evaluate? So we took the data from the ICU. We have some policy that we came out somehow. We did deep Q learning, whatever. How can we evaluate its value with U as unobserved? And anyone trying to do optimal dynamic treatment policies with observational data has to answer this question. And the answer in general is that this is impossible. You cannot evaluate, in this scenario, you cannot evaluate pi of ZT. It's severely under-identified. Okay. Questions? So just some notation, we'll denote P with the superscript pi B of things will be data from the observed behavior policy. We can sample, or something that is we can sample from this distribution. We have access to this distribution. And P pi E is the targeted evaluation policy that we cannot sample directly from this distribution. We assume it shares the same transition kernels. It shares the same black arrows, but these arrows are different, which makes everything possibly very different. Okay, so without further assumptions, this is impossible. For example, and this is a real example that happened with people who did reinforcement learning in ICU data, ICU doctors basically treat sicker patients more aggressively. How much a patient was sicker was not fully reflected here, and the reinforcement learning algorithm learned that you should not treat patients aggressively. Because if you treat patients aggressively, they die. That's what you see in the data. But of course, they don't die because you treat them aggressively. They die despite the fact you're treating them aggressively. And just their data was not good enough. And, well, they had many problems, okay? So that's an example. And in general, this is impossible, even if you condition on the entire observable history, okay? It's just due to the hidden confounding. This is kind of a basic causal inference result. So this is much harder than standard causal inference because you have these confounder action dynamics. So you don't know why something happened, and then it leads to a different state, which you don't know why you're in, and so on and so forth. So this is actually much more difficult than standard hidden confounding because of the dynamics that induce these long-term dependencies once you don't have U. Because without U, this is not Markovian. Okay? So this is a very hard problem, and to the best of our knowledge, and I'll be happy to hear from you if you know otherwise, no one has actually looked at off-policy evaluation in a POMDP, in a partially observable process. So we think we're the first, but I might be wrong. So we have to make some assumptions, of course. And we'll see what we do. So here, to our help, came this very nice paper, came out a year and a half ago, actually it was 2017 on arXiv, from causal inference. So this is from Gang Miao and Eric Chetgen-Chetgen, Miao, Gang, and Chetgen-Chetgen. They're from epidemiology and biostats. And they have this very nice result. They're saying, let's assume I have this causal graph. I want to know the causal effect of A on R. And I have hidden confounding U. Okay? If I just have, without the Z and W, just this graph, is obviously it's like the canonical non-identifiable causal effect. But they assume we have Z and W. Okay? And moreover, they assume that Z and W are conditionally independent of U. So you have these proxies for U. You don't see them. You don't see U, but you have these proxies. And you have two proxies. And this is still not enough, but they have a new condition which we found interesting. And it's as follows. So we have to assume all of these U, Z, and W are discrete variables. And now they define this matrix. The ij matrix, the ij entry of this matrix is the probability that w equals y conditional on z equals j and the action is a. Okay? This matrix can be estimated from the data. W, Z, A are all observed. If these matrices for all A are invertible, then turns out you can calculate the causal effect of A on R. Okay? So this requires two things. One, that these matrices are invertible, and that WZ are discrete with as many categories as the discrete. Okay? We're going to use this idea in our case. How do we do this? We'll assume Z are discrete with as many categories as UT. Okay? This is untestable assumptions. If someone, usually in causal inference, you have to look for the untestable assumptions. If they're not there, they're there. They're just maybe people are not telling you them. And we define similar matrices, which are the probability of ZT equals I conditional on ZT minus 1 equals J. So this is the future and the past and the action. And what we can prove is this: if these matrices are all invertible, we can evaluate the value of proposed policy pi e with observational data. Okay? So we have a condition for identification. Okay? And the basic idea is that the future and past observations are conditionally independent proxies for the unobserved U. So we don't know U, but we have these proxies, Z, these two Zs, which can act as proxies. The structure here is much more complicated than in the Chetkin paper, but still, it can work. And just some intuition about this invertibility conditions. So if the ZT are binary, then a sufficient condition for invertibility is just that the conditional of ZT equals 1, condition on ZT minus 1 equals 1, is not the same as the probability of ZT equals 1, condition on ZT minus 1 equals 0. Okay? This is enough for this 2x2 matrix to be invertible in the binary case. Okay, so invertibility is not such a strict assumption because the set of invertible matrices is, for example, full measure of full measure. The difficult assumption is that Z has as many categories as U. That's the untestable assumption. Okay, so any questions about this? Okay. So under these two assumptions, we can do off-policy evaluations for a class of POM-DPs. And we have no need to measure we don't need to know what's U. We just need to assume it's not too complicated, that Z has enough categories as U. And again, we don't assume much about, basically what we assume about this arrow is that it encodes an invertible matrix. But note that this does not mean that this is a linear operation. That just means that the joint probability distribution is an invertible matrix. Okay, so just how do we do this? I will go over this very quickly because it's nasty. Let's say we have a sequence of observations and actions. We define this matrix, which is something joint distribution. Then we define this matrix, which is the inverse of M times this. Then we do a bunch of more matrices and vectors and multiply many matrices together, and so on and so forth. We end up with some pretty ugly expression, which only use things we can measure, because these are all pi b, and here we only use our evaluation function in the sense of what action do we do conditioned on the observables, so we know this. Okay? So this is correct in the sense that this allows us to identify. It's not very good in the sense that we have to, if we have finite data, which we usually do, we need to estimate all these matrices and then use their inverses, which is not good. Estimating the inverse of this matrix is hard. So this scales poorly statistically. So we have another model called a decoupled POM-DP, which is better statistically. We still need to estimate inverse matrices, but they're much nicer inverse matrices. I will not go into the causal graph, but this is the causal graph of the decoupled POM-DP. It is more, in a sense, it's more general than the POM-DP. I just want to say that we have some solution, a partial solution, But we're still not very happy about this as a practical algorithm. So I care about making these things practical. I work with physicians and I want to help them. This still scales poorly, not very well statistically. We still need to estimate many of these joint matrices and their inverses, and we multiply all of these inverses together, so this still doesn't behave very well, even if the matrices are nicer. So my current challenge is, basically I'm trying to think, how do I take this idea and make it maybe less theoretically grounded, but more practical? But still, this is, to our best knowledge, the first kind of non-trivial POM-DP off-policy evaluation result we have. Okay, questions about this one? Okay. So I'll have a bit of time, at least for this last thing. All right, so wait, how much time do I have? Is it 5 minutes or 15 minutes?
5, and then we have 10 minutes.
Okay, 5, that will be hard. Yeah, I'll just do a tiny bit of this. So I won't go into it. This is work with colleagues from NVIDIA. And I'll just give you the problem. What is this? What are we seeing here? Cauliflower. What color is it? Purple, kind of pink purple. Has anyone seen a purple cauliflower before? Yeah. Here you see it. And no one in Israel has ever seen this. I mean, people thought it's photoshopped, but it's real. So what I do in Israel is I say, okay, you know, people even in Israel who've never seen this know this is a purple or pink cauliflower. Because we know it's a cauliflower and we know about purple things. So even if we haven't seen this combination, we're still doing this pretty easily. Oh yeah, I have it. So basically, again, this goes back to what I talked at the beginning. We want our algorithms to be able to recognize these new compositions, new combinations that are not, maybe not seen in the training set. Skip this. So humans often easily identify these previously unseen compositions, okay? And our assumption is that where does causality come in? It comes in as an inspiration. Okay, here, this is not rigorous. But it says there are two different mechanisms. There's the mechanism of being a cauliflower, like an object, which generates distributions of pixels. There's a separate mechanism, which is color, or more generally, attributes pixels. And we can think about them as separate mechanisms, which can be composed. You could imagine a black cauliflower, a yellow cauliflower, whatever. Even if you haven't seen one, you can imagine that. Because, again, informally speaking, these are separate mechanisms that can be composed, okay? And we humans often do this easily, okay, like the purple cauliflower or the spotted elephant, okay, which I imagine most of you haven't seen. I don't know if this is a real elephant, but we have no problems recognizing. Or even something like a monkey riding on a pig, okay? You can imagine this in your mind, even if you've never seen this guy, okay? And we want our algorithms to be able to do this because humans do this easily. And algorithms currently mostly could recognize pigs and monkeys, but like this will confuse the hell out of them. Okay, so the task is recognizing unseen object attribute pairs. So specifically, the task we focus on here, and I will not say how we do this, but given a set of, let's say we know the universe of objects and the universe of attributes, for example, colors, let's train on some set of combinations and test on a different set, okay? So our test set will be images with previously unseen compositions, okay? So you may have seen a monkey and a pig, but you've never seen them in that way together, okay? And correlation-based methods could easily fail. So this is a real example for on paper. So you have this black goat, and in the training set, there were no black goats by design. That's how we designed the training set. And if you have a separately trained object and attribute classifiers, what it says, it identifies this as a black object. That's kind of easy, but it thinks it's a dog because it's seen black dogs, and color is very salient to these image recognition methods. And our method does, the methods that I will not have time to explain, actually does get this successfully. And the way we do this, I'll just give our inspiration, and then I'll stop. We consider this causal graph of an image, which says there's an object and an attribute, and they both separately right? They're separate mechanisms. So for some things, it makes sense to separate them, like color and object. You have the core object features and the core attribute features. Now, objects and attributes are correlated or confounded. Tomatoes tend to be red, so they're not uncorrelated. But we want to learn a model that will be able to, in a way, be stable against interventions on this edge. We want to identify black tomatoes or black goats or spotted elephants, even if we haven't seen them in the training set. Okay? And the way we do this is we basically read off a bunch of independent statements from this graph and use them as inductive bias to a deep learning method. Okay, so we train a deep learning algorithm which learns representations, and we try to make all of these happen. We use two technical tools. One is the Hilbert-Schmidt independent criterion we saw earlier, which helps us for conditional independence, and adversarial networks, which also help us. And we try to learn to generalize to unseen compositions. We do this with some success. I will not go into the details of that. And like this is neural network, so there's big architectures that you can look at. Okay, so skip this. And I just want to say, because also there's some work from here, ETH, coming about all these papers which try to learn conditionally independent distributions, representations for fairness, for causality, for all kinds of things. This is just a sampling of many papers in the last few years trying to learn conditionally independent representations. And the hope is that if you're conditionally independent to something, you are robust to something. Okay, so, and I think it's interesting to think about it as a more general problem, saying what is independent of what, conditional on what? How do you measure conditional independence, or how do you encourage it? There are many different ways. How do you robustness or fairness or causality? How do you measure these? You could think about fairness and causality as special cases of robustness. And when can we prove something? So this work I didn't go into, but it's very much let's hack the neural network this way because this might be helpful. But how can we be more rigorous? When can we say that conditional independence of some sort is small, then robust error is small? Like under what conditions can we say that? There is definitely work on that, but I think there's more to be done. Okay. So just to sum up, causality-inspired machine learning. So first idea was for the independence of cause and mechanism gives us a learning objective which is useful for unsupervised covariance shift. Right? We said in the causal direction, the residuals are independent of the causes, and we can use that to learn a robust model. We use something called negative control for causal inference to create the first off-policy evaluation scheme from POM-DPs, where the past and the future are the proxies or the negative controls in the causal inference language. We saw just a hint of using the causal graph as an image as an inspiration for a deep learning method that can generalize to unseen object attribute compositions. Yeah, and I just want to thank all my collaborators from the Technion, NVIDIA, and other places. And thank you for your time and your attention. Thank you very much.
So yes, we have time for a few questions. Domagoj will throw you the ball.
Oh, come on. Okay. So for the first thing, like for the kernel independence thing, I was wondering, how do you choose? Oh, sorry. How do you choose the kernels, and how important is that for the practical application?
We mostly used RBF kernels. Our theory says they should be nice. We did play a bit with other kernels. In the other work, we actually use linear kernels, because if you're learning deep representations, maybe even a linear kernel could make sense between them. But we haven't tried anything fancier than RBF and linear kernels.
And for the second one, like you make a lot of assumptions for this whole off-policy POM-DP thing, and I guess for like real-life medical applications, some of them might be not realistic yet. So what do you think is the kind of assumption that would be most valuable to loosen a bit, like if you could
for like a real application?
My problem is less with the assumptions and more with the method we ended up with, which I think scales poorly statistically. I think we don't really need to estimate these inverses. I think we can approximate that in a more direct way if we had a model of the reward. We don't have any model basically of the reward, and that is probably wasteful. And maybe a good assumption is hiding there as well that will help us once we go into that.
Okay, thanks.
Yeah, thanks for the talk. I was wondering for the attribute and the last thing you talked about, what kind of data set were you using there? Were you having attribute labels at the same time, or just
Yeah, we had two data sets. We created a data set called which has very nice objects and attributes and validated it with humans, and we'll publish this. We also use something called Zappos, mini Zappos from shoes. We found this data existed and people use it for zero-shot learning. We found it to be super, super noisy. The labels, people had 30 or 40% agreement on the labels. So we created a subset of it where agreement was somewhat higher, like the cleaner part of this data set.
Okay, yeah, thanks.
Can you explain a bit the assumption that ZL, sort of this dimension of ZL must be bigger than sort of the dimension of UL? I mean, doesn't it imply, my question is, does it imply that UL is in a certain sense perfectly known through ZL, or?
No, it doesn't have to apply. So imagine, first this is not, it's confusing. It's not dimension exactly. Where is this? It's not the dimension, it's that they're discrete with as many categories. And that's actually an important distinction. We assume Z has as many as U, but it doesn't mean U is known. So imagine, like, you can have a very much a mixed thing, right? Imagine a 2x2 conditional independence table. Basically, we just need it to be not half, 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 half. If let's say the marginal on U is half and half, you need Z condition on U to not be half and half. Anything else will work. So you can mix them a lot. It does mean that we're not mixing them all the way, right? We are keeping some information, but we don't need to keep a lot of information. But we have to make, we have to make some assumption along those lines that there's some information from U and Z. So this is the way we do that.
And I guess what prevents me from just adding a dummy category, like so as to be bigger, is matrix invertibility condition.
Because if you have just a dummy category, these two kind of act against each other. If you have a dummy category, it will have probability 0, unless I give it probability and then I take away from probabilities of the other, right? And that's why it's important to not think about it as dimensions, but as one variable with a set of categories. We could take just one category out of these.
Okay, thanks.
Thanks for the talk. You mentioned that some of your students wrote guidelines for using reinforcement learning in healthcare. Could you mention some of their main points?
Yeah. So these are not my students. These are my former collaborators and former advisor from the postdoc. So two things that in causal inference are very basic. Consider hidden confounding. Consider factors that affect the actions and the rewards and are not in the data. Think about them. If you have them, maybe you can't use your fancy reinforcement algorithm. That's one thing. The second is, again, something basic in causal inference, which is overlap or common support. You need to be, if you're trying to evaluate a policy, which is very different from what the doctors actually do, you have no data to use for that. Okay, so you need your policy to not deviate too much from the observed policy. Maybe it's better, but you have no way to know it. So you have to be careful about that. Otherwise, you have, I don't know if you're familiar with importance sampling, but you have these many zero weights that really change your distribution.
Okay, thank you.
In your example for the spotted elephant and the monkey on the pig, and its connection to imagination, my conclusion would have been that the spotted elephant is either a doctored picture or somebody put stickers on it, and the monkey on the pig is possible. So there was both this imagination plus some analytic thinking that came afterwards. How do you actually incorporate that if you actually want to get to that point?
I'm trying to do something much more humble. I think it's a good question. It's a difficult. I mean, you think it's doctored, the spotted elephant, but my daughter, who's 7, might think it's real. She doesn't yet know for sure there are no spotted elephants. So that's really high-level knowledge. You need a lot of interaction with the world to be sure there are no spotted elephants. So we're trying to do something much simpler, which says most humans would agree this is both this is an elephant and spotted. Experienced humans will know more, but even just that, current image recognition systems might easily fail. Just recognizing those basic things that humans easily do. So I first want to get that. The harder questions, let's talk in 10 years.
Okay, we're out of time, but there's the apero outside, and Uri will be around for a bit if you want to ask further questions offline. And then let's thank the speaker again.